We have done collisions in one dimension, so now we're going to do collisions in 2 dimensions. The sorts of problems we run into the most with this are car problems. Let's have a car with a mass of 4 kilograms moving along at, maybe 2 meters per second. And that's going to run into a car. These are toy cars, clearly, of 1 kilogram. And we'll give this one a speed of 6 meters per second. They are going to run into each other, and there will be an old-style comic book crash right about here. After which the two will be kind of mangled together. So 4 kilograms, 1 kilogram, this is going to be 5 kilograms. And that's going to be moving along at some angle. Now we can do problems, v final equals question mark. We can do problems where they bounce off each other and we have a 2-dimensional bouncing off collision or glancing type of collision. I will talk about that briefly, but it's not the kind of problem that you're really going to be asked to do, so I just kind of want to touch on it a little bit. Final velocity. We are no longer working in 1 dimension, so now we have to take into account that this is going 2 dimensions. I'm going to break this final velocity into 2 components. I'm going to say here is an angle. Here is v final y equals v final times the sine of theta, both of which are unknown. Here is v final x, which is v final times the cosine of theta. V final and theta are both unknown. I'm trying to keep those in red, just to be clear about that. So I know how to do this problem in 1 dimension. I just take my initial momentum, set it equal to my final momentum, and solve. I'm going to do the same thing here. I'm going to say, in the x direction, because this is a vector, because momentum's a vector, I can preserve and conserve my momentum in x and in y separately, and then put them back together at the end. So my initial momentum in the x direction, this one, 4 kilograms times 2 meters per second. This one has nothing, it's all in the y direction. So I've got 8 kilogram meters per second. What I should have said right from the start is I'm calling to the right my x direction, and I'm calling up my y direction. So that's what I've got in the x direction. My sum of momentum final is going to be 5 kilograms times, and I can even just solve for this way. I can call this v final x. I can set those equal to each other. 8 kilogram meters per second equals 5 kilograms times v final x, and that gives me v final x is 8 over 5 is 1.6 meters per second. That's not too bad. Now let's try y. In the y direction, I'm going to do the same thing. My sum of momentum initially, I've got nothing from the first guy, and the second one, I've got 1 kilogram times 6 meters per second gives me 6 kilogram meter per second. My final momentum, I'm going to have 5 kilograms times v final y. And then I'm going to set those equal to each other. 6 kilogram meter per second equals 5 kilograms times V final Y. So V final Y is going to be 6 over 5 is 1.2 meters per second. I'm looking for the speed after the collision and the angle, but I now have the components. I know horizontally I'm going 1.6 meters per second. I know vertically, I guess not vertically, just in the y direction, right? This is like a collision looking down from above. I'm going 1.2 meters per second, so maybe east and north instead. I want my diagonal like that. And I want my angle right there. So V final is going to be the square root of 1.2 meters per second squared plus 1.6 meters per second squared which works out to be 2 meters per second. I would like my angle, and my angle will be an inverse tangent of 1.2 meters per second over 1.6 meters per second. That is 37 degrees. And I now have my answer. I know how fast I'm going after the collision. I know in what direction I'm going. If I had a glancing type of collision, which does happen, but we're not going to really worry about it much here. I just want to show you kind of what that would look like. So maybe I've got object number 1 that's coming this way. It's going to run into an object number 2 that's going this way. I'm going to connect these with some kind of a line. This one wants to go this way, this one wants to go this way. So in the middle, when these collide, they are not colliding on their centers. This one will end up going off that way somewhere. This one will end up going off that way somewhere. This would be V1 final. This will be V2 final. If you ever came across a problem like this, it is almost certain that you would be given all of this information, all of this information, and all of one of these two. When you've got all that, then it's just a matter of doing the exact same thing as before. And it's not bad at all. It's just recognizing, but these types of problems don't come up very much in a trig-based physics class. They come up a bit more if you are continuing on with physics really beyond this point. When you start to get into the more calc-based physics classes, then this comes up, unless you're given just a ton of the variables and asked for the last missing piece. So that's it. That's collisions in 2 dimensions.